Hello, everybody, and welcome to our presentation on utilizing Arm CMSIS-NN to optimize a neural network compiler. And we'll get into some of the technical details and some of the highlights of this technology so that you can really get an understanding of how this thing works. My name is Markus Levy. I'm the Director of Machine Learning Technologies at NXP.
Hello, this is Ciprian Mindru. I'm a software engineer at NXP in the Bucharest site, and I was part of the staff who worked on utilizing Arm CMSIS-NN to optimize a neural network compiler.
So before we begin on the details, let me just give you some of the motivation behind this. And you can see on this chart here, it's doing a high-level benchmark comparison using a CFAR 10 benchmark, which is a relatively simple benchmark, but it does allow us to highlight the fact that using the optimizations that Ciprian and his team did, we're able to get almost a 2x performance increase over the out-of-the-box version. And what I mean by out-of-the-box here is that since GLOW, as the neural network compiler is an open source technology, you can easily download this from the GitHub or repository, and you could try it out in a very unoptimized manner, but at least allows you to see the functional operation of this. So that's what the 6.05 frames per second is, but by the time you add in the CMSIS-NN backends to optimize for the Cortex-M CPU core, you get almost a 2x performance increase. So before we begin on the GLOW technical details and talking about this neural network compiler, let me just give you a high-level overview of the device that we used as one of the targets. This particular diagram here is the RT1060, and the key points to note for this particular presentation is the CPU platform, which is a Cortex-M7 that runs up to 600 megahertz. We have new devices that are on the horizon, specifically the RT1170, which has a 1 gigahertz core on that. So you could imagine that you get a very significant performance increase. And this is just on an MCU, right? So having 1 gigahertz of performance is pretty amazing for an MCU platform. So also a little bit of the overview of NXP's broad machine learning solutions. And this slide will highlight some of the key functions that we enable. So if you look at the first build out here, this is a do-it-yourselfer. So EIQ, which is our machine learning support, is all about allowing you to bring your pre-trained machine learning models onto our platform and run using some form of open source technology such as TensorFlow Lite, Arm CMSIS-NN, GLOW, ONNX runtime, etc. We also engage very heavily with third-party software and hardware vendors. This is just a small list of the companies that we are involved with that provide complementary technologies for our EIQ enablement. We also have a group that is providing turnkey solutions, and some of the examples you see here are for Alexa voice services or local voice control solutions that provide both a hardware and software combined solution that allows you to drop this into your platform. And lastly, there's another side of our business here that is very heavily focused on the automotive, and they provide their own EIQ Auto tool, which provides optimizations, pruning techniques, quantization, etc., and it provides a automotive quality inference engine that many of our automotive customers require. So now let's get into a little bit on the neural network compiler itself. So first of all, this is extremely basic, but this is what a very simple neural network looks like. And as you probably are familiar already, it's comprised of these nodes that are connected in various links. And basically what happens is you put the input in, it could be an image, it could be a video frame, it could be sound. It processes, and at the output of this will give you some level of confidence as to what that actual input was. So in the sense, it's making a decision or some type of a guess on what it is. But the point here is that these nodes are all connected together to provide more of like what some people might consider to be like a brain-like function. Now, looking at it a different way, these nodes are all represented by layers, and those layers represent various operator functions such as convolution, ReLU, pooling, fully connected layers, and then finally on the output, you'll typically would have like a softmax layer, which is providing the decision factor. The point of this slide here is really to demonstrate that a machine learning model is comprised of multiple layers, and typically, you'd find somewhere between 50 and 150 or even more layers, and each layer is comprised of many millions of computations. So it's pretty heavy-duty processing to do a machine learning model on a device, especially an MCU. Now, we're getting into some of the GLOW fundamentals. First of all, let me point out here that in a typical processing fashion, a model is executed using a runtime. And in this case, it's demonstrating a TensorFlow Lite runtime. Now, the point here is that TensorFlow Lite and all runtimes, including Arm CMSIS-NN and ONNX runtime, are dynamic processing engines. And so it looks at each layer one at a time as it's processing it. So it's a very dynamic process. All of the work is happening during the runtime part of it. So the CPU core not only is processing the runtime engine, it's also processing all the operator computations. So you can see that using a runtime engine like TensorFlow Lite, the processor is very busy. Now, if you compare that to how GLOW works, GLOW, and Ciprian will get into more details on this, GLOW allows you to do ahead-of-time compilation, which is similar to any other type of compiler that you may be familiar with. So GLOW takes the model during the development phase and actually goes through all the layers, and it looks at both global and local optimizations to produce object code, which is then run as a sequence of computations on the platform. So there's no runtime component associated with it.
Okay, so I will talk about a couple of methods for deploying GLOW. There are multiple ways to deploy a model using GLOW. One way is to use PyTorch, which is an open source machine learning framework developed by Facebook, which is widely used in research. PyTorch can be used to train a model and compile it directly with GLOW, since GLOW capabilities can be accessed directly from PyTorch. Another way is to use a TensorFlow, which is an open source machine learning framework developed by Google, which is widely used in production. TensorFlow can be used to produce a TensorFlow protobuffer format, which can be converted to ONNX, which stands for Open Neural Network Exchange format, and then directly imported with GLOW. But TensorFlow can also be used to produce a TensorFlow Lite flat buffer format, which can be directly imported with GLOW. By using any of these methods, the model is then passed on to the GLOW backend, which performs target-specific optimizations for NXP devices. For targets using ARM Cortex-M devices, the GLOW backend provides integration with the Arm CMSIS-NN library. For targets using the Cadence Tensilica Hi-Fi 4 DSP devices, the GLOW backend provides integration with the Hi-Fi NN library. The final product of the compilation chain is the so-called bundle, which is a self-contained library, which can be directly compiled by the toolchain, along with other application object files. Next, a couple of words about the two possible ways in which GLOW can generate the code required to run on the target. The first way is the so-called just-in-time JIT compiling. This is the approach used by most software frameworks. In this case, the GLOW software runs natively on the target device. The neural network model is transferred from the host machine to the target, where GLOW compiles the model in machine executable code while also executing it. This technique of compiling a program while also executing it is named just-in-time compilation or dynamic translation. This approach is flexible in the sense that all that is required from the host machine is to provide a pre-trained model with no extra intervention, and also dynamic in the sense that the model which runs on the target can be replaced easily on the fly without interrupting the target from running, for example, with a new model with potentially better performance and accuracy. Also, the model could as well be provided from a cloud database, thus being suitable for cloud computing. On the right-hand side of the slide, we see the other way, which is the so-called ahead of time, or AIoT. In this case, the Glow software runs natively on the host device, where it cross-compiles the model into a library, which is later integrated with an application and transferred as machine executable code ready to run on the target. This technique of compiling a program before executing it is named ahead-of-time compilation or static translation. This approach has the benefit of an improved memory footprint, since the target code does not include the Glow runtime, but only the inference library, which contains the minimal amount of code and functionality required to run the model. This achieves a significant memory optimizations, which is suitable for memory-constrained devices, for example, embedded devices like microcontrollers. One drawback is that this method is static in the sense that in order to replace the model running on the target, the intervention of the host machine is required to compile a new application code, and also the target must be interrupted to load the new program. Next, I will show you a couple of things, which is basically the compilation pipeline, which is done by Glow. So Glow achieves the translation between high-level mathematical operators and low-level machine instructions through a technique called graph lowering, which is used in conjunction with the LLVM compiler infrastructure. First, Glow analyzes the model graph of the neural network and maps each layer to high-level mathematical operators, which in Glow terminology is called a node. Further, each node is lowered, that is broken into smaller fine-grained operations called instructions. This lower-level representation is memory-aware in the sense that instructions operate on data values which are referenced by address. This enables low-level memory optimizations that are not possible in the higher-level domain, where memory is not represented directly. Also, this representation is time-aware, since at this level scheduling occurs. Next, the so-called Glow instructions are further lowered to the LLVM internal representation, which is the internal language of the LLVM compiler. Up to this point, every representation is hardware independent, such that the final stage, the final step, is to hand over the LLVM representation to the LLVM compiler, which does its magic and generates optimized machine code for the desired target architecture. Next, a couple of words about how to use basically this technology. So the Glow compiler technology can be used through command line front-end tools, which are available for both the Linux and the Windows environment. We have the so-called model compiler utility, which is used to cross-compile a model for a given target device. Next is the model profiler, which is used to quantize the model before compiling it in order to achieve a better memory footprint, around 4x improvement. And optionally, we can use also the model tuner, which can be used to optimize the quantization process for better accuracy. Glow can import directly model formats like Caffe2, ONNX, and TensorFlow Lite. Other model formats can be used indirectly by using converter tools like MMDNN or TensorFlow to ONNX to convert various model formats to those directly supported by Glow. When a model is compiled, Glow basically generates a bundle, which is a collection of the following artifacts. It's a .o file, which is a self-contained bare metal software library, basically binary object file, which has no operating system requirements or other runtime dependencies. Also a .h file, which is an auto-generated header file, which exposes the library API, that is the interface. Weights.bin file, which contains the model weights serialized in binary format, and the same content as weights.txt, which contains the same model weights, but this time serialized in text format, which allows including the model weights in an application as a simple C array. Apart from using the ahead-of-time compilation in order to reduce and improve actually the memory footprint, we also have this mechanism and technique, an important technique called quantization, which is used to further improve the memory footprint. The quantization process consists in transforming the model in order to use small integer operations, for example, 8-bit integer operations, instead of the usual 32-bit floating point operation, thus achieving a 4x memory optimization. From the user perspective, in order to compile a floating point model without quantization, one would simply use the model compiler command line tool, as suggested on the left half of the slide, which is provided with the model file and the compile options in order to produce the bundle. On the other hand, as suggested on the right half of the slide, in order to quantize and compile a floating point model, one would need to use first the model profiler command line tool, which is provided with the model file and some sample input data, to produce a profiling information file in IML format, which contains all the required information in order to properly quantize the model. And then only after that, one would need to use the model compiler command line tool, which is provided with the model file and the profiling information previously obtained, but also the compile options like target architecture or whether to use CMSIS or not, to quantize and compile the model in order to produce the final bundle. Next, I will talk about the actual optimizations we did. Up to this point, everything was generic. So up to this point, everything is basically Glow out of the box. A couple of words of what we did in order to optimize Glow for the NXP devices. So first of all, CMSIS-NN, a couple of words about CMSIS-NN. So CMSIS-NN is a software library, basically a collection of efficient, manually optimized kernels, which are developed to maximize the performance by using specialized hardware instructions like SIMD, that is single instruction multiple data, which are instructions capable to process multiple data operands at once, and also to minimize the memory footprint by mostly using 8-bit integer operations. So CMSIS-NN is developed for Arm Cortex-M processors and includes kernel implementations for the most common operators found in neural networks like 2D convolution, max pooling, average pooling, fully connected, activation functions, and also some utility functions used for data type conversions. But it is important to note that CMSIS-NN is not all-encompassing, meaning that CMSIS-NN does not necessarily have support for all the operators which can be found in neural networks. So what we did with the CMSIS-NN, basically we integrated this kernel library within Glow. Glow, on one hand, has its own kernel library with generic implementations, which are not tied or optimized for a particular hardware. So in order to optimize, accelerate the out-of-the-box performance of Glow, especially for Arm Cortex-M devices, we integrated the CMSIS-NN library within Glow's internal graph optimization pipeline, using the following logic. So if a given graph operator within the initial model graph is supported by CMSIS-NN, then Glow creates a function call to one of the CMSIS-NN kernels. If not, then the default kernel implementation used from Glow's internal kernel library. By doing this, the following benefits emerge. So basically, operators within the graph supported by CMSIS-NN are specialized, resulting in better performance. But on the other hand, operators within the graph which are not supported by CMSIS-NN are compiled using the default Glow implementations, ensuring that the model can be compiled and executed.
Okay, so I know that was a condensed version of the Glow technical details, but now let me just get to the real punchline here. What benefits does Glow really bring? And you can see in this slide, again using the CFAR10 benchmark, a comparison of the optimized Glow with CMSIS-NN integrated compared to the TensorFlow Lite implementation. Now, mind you that TensorFlow Lite is also, very progressively being improved. So these numbers will change over time and probably have already changed since the development of this presentation. But suffice it to say that there is a significant performance increase of using a runtime versus the compiled version of GLOW with the optimized CMSIS-NN backend. So you can see right off the bat that you get a 3x increase using this RT1060. Now, if you also scale up to the RT1170 with a 1 gigahertz core, you get a linear improvement on the performance here. So pretty substantial increase. Now, where you also see benefits, as Ciprian pointed out, due to the quantization factor, is the difference between memory sizes. And you can see that the memory utilization for GLOW is 2 orders of magnitude lower than with the TensorFlow Lite. Now, mind you that the benchmark used for the TF Lite was also quantized, so we are more or less doing an apples-to-apples comparison, but you can see that because of the overhead of the runtime engine versus the compiled mode of GLOW, that the memory savings is very substantial. So on that note, I want to thank you very much for listening to our presentation, and if you have any questions, you can contact us directly. Thank you again.